We're barely getting into it. We got a lot. Okay, so common types of reactions, things like combination reactions. Combination reaction, pretty simple, straightforward. A plus B will produce AB, right? So that's a common type of combination reaction. H2 plus O2 produces H2O. So you put two things together, they form something new. Decomposition is essentially the opposite. AB decomposes into A plus B. So here we could just write this H2O decomposes into H2 plus O2. And that would be decomposition. It's breaking apart. It's coming apart. That's not an N, by the way. That's an H. Okay. Single replacement and double replacement, those are mostly identified with, not always, but for the most part, they're identified with reactions having to do with ionic metals or compounds. So for example, you have copper. It's solid copper plus, right here, let me just write it in AB terms. So you have A, and it's a solid, plus CB, okay? And what will happen is that A, and this is probably an aqueous thing. Does everybody know what I mean when I say aqueous? It's dissolved into water. That's what it means. It's a solution. It means CB are actually broken apart into their ionic constituents, but they're dissolved into water. That's what that means. Okay? So they're not actually together. They're broken apart. Okay? And then you take a solid thing, whatever A is, it's a solid metal, you put it in, and it's going to react, and it's going to switch places with C. And C will come out as the solid, and you'll be left with AB aqueous. Okay? So that's what that means. This is a metal, and it's switching places with this metal. It's a solid, but it will begin to become ionized. And what do metals do to become ionized? Do they gain or lose? They lose electrons. So A has all of its electrons. It begins to lose. So let's say that A is, well, in this case, we're actually going to say it's copper. Okay? So it's copper, and it loses 2 electrons. Okay, let's say it loses to go from copper solid to copper 2 plus. Okay? So it loses those 2 electrons. And now it gives, well, how did it lose them? It can't just lose electrons, right? Something has to force them off of it. So what forced those electrons off of that? C did. C's missing electrons. Right? It's a metal that has electron deficiency. And so it pulls the electrons off of A, causing it to become ionized and dissolve into the solution, whereas C gains those electrons and begins to precipitate out of solution as a solid. Okay? So it's switching place. Well, how does it do that? It's because the potential for electrons, for this guy to gain electrons, is higher than this guy's. And so it pulls them. It pulls those electrons. And we're going to talk about that. That's called oxidation and reduction. We're going to have a whole section on oxidation reduction in this chapter that we're going to talk about in more depth. Okay? But that's what's happening. That's a single replacement reaction. An example of that would be copper solid plus silver nitrate. So we have silver. This is silver 1. Silver is always silver 1, right? Always has a +1 charge. This is nitrate. Nitrate has an NO3 minus 1 charge. So they come together in this ratio. And they are aqueous, meaning that it's actually Ag plus NO3 minus in solution. Okay? If they're in the water, they have broken apart, just like any ionic compound would do when dissolved into water. Okay? So this copper is going to give its electrons to silver. Silver has a higher potential for electrons, a stronger potential for them. And it pulls the electrons away from copper towards itself. So, what's going to be the products of this reaction? Good. So we're going to get silver solid plus copper nitrate. And to the correct ratios, because this would be copper 2, most likely. So we need a copper 2 plus NO3. Okay. Okay, so that's how this would work. Do you see any benefit in that? Take a piece of copper, a copper wire, put it into silver nitrate. What do you get out? Solid, pure silver. Okay? That would be pretty lucrative if you have a nice source of silver nitrate somewhere. You go find it. In the ocean, they have all this gold dissolved in the ocean, aqueous gold. They want to pull it out. Okay, so they want to do these kinds of processes, pull out all the gold, all right? And it could be lucrative for them. So maybe you guys will figure that out. One of you geniuses, you're going to figure that out. Okay. All right, so double replacement. Same as single replacement, just now instead of working with a solid here, I'm working with two ionic compounds. Okay? So once again, I have something like lead nitrate. Okay? Plus sodium chloride. Okay? So it's two aqueous solutions. This is aqueous. This is aqueous. They're both clear. So if I had two test tubes right here, they're both clear. One of them would be lead nitrate, and one would be sodium chloride, aqueous. You can't tell the difference between either one of them. Okay? They look like they're just water solutions. That's why you don't ever drink anything in the lab, right? Because lead's toxic and you would die if you drink it. So you pour those two things together, all right? And what are they going to do? Well, if it's a double replacement reaction, that means the cations are going to switch. So lead is going to come here, and sodium is going to come here. What are the products of this reaction? Sodium nitrate and lead chloride. Now the question is, if those are my products, the question is, do they just remain dissolved? They're both ionic compounds again. They started as ionic compounds, and they're both ionic compounds in the end when they switch partners, right? So, do I write aqueous on both of these? That's the question. And the answer is maybe not. Because there's a certain chart that we're going to look at when we get to this precipitation reactions, we call them. And it's going to tell us if either one of these is a solid product. Because if there is no solid product, meaning if I just write these as aqueous, then nothing actually happened, right? They were all dissolved before. You pour them together and they remain dissolved. Nothing happens. There's no reaction. But if one of these turns out to be insoluble when I form them, then there's a reaction, and that is a product. It will be a solid, and lead chloride happens to be a solid precipitate. This one will precipitate out, nice yellow precipitation, and it will come out a solution. And all the other stuff, the sodium and the nitrates, they just remain dissolved. They don't do anything. They are aqueous still. They are not a solid. So they just stay in there. They don't do anything. So this is a double replacement reaction where the two cations are switching partners. Why is it that it could not have been, potential products could not have been lead, sodium. Let me just write it like that. Why could that not have been? Or what about this one? Or chlorine nitrate. Why can't I have that? Why can't I have this or this? Because of what? Well, the valence electrons might have something to do with it. But what has more to do with it is what kind of ion is lead? Cation. What about sodium? Okay. So now, do you see why? Why can't they come together? They do switch. They repel each other. Think of a magnet, right? The positive poles of a magnet, if you push them together, what happens? They're not going to come together, right? They're just going to bounce away from each other. That's exactly what these would do in solution. They would never get by each other. They would just simply repel one another. What about these guys? -1, -1. They would just repel each other, right? The only way you can get them to come together is having opposite charges, right? A negative and a positive charge coming together. That's how they'll attract, just like a positive and negative pole of a magnet. They will attract one another, and that's how they come together. Okay? So these could never be the products of this reaction. So that should help you see how to figure out what are the products of this reaction. Well, the only things I could get is, other than what's already here, is sodium nitrate and lead chloride. And the cation ion, the positively charged ion, is always in front. It's always first. Okay? So those are the only two potential products that I could get from this reaction. I couldn't get it any other way. Okay? So that's how you would predict the products of a double replacement reaction. And double replacement reactions are precipitation reactions. Or I should say precipitation reactions are double replacement reactions. But also single replacement can have precipitates. Just a different one. Okay? Acid-base reactions. Acid and base reactions occur with the transfer of hydrogens. H+. Okay? The hydrogen is being transferred from one thing to another thing. So whenever you're working with an acid, it should always have a hydrogen on it that can be transferred. HCl. That's a strong acid. HCl has a hydrogen that can be transferred. Sodium hydroxide. This is a base. Sodium hydroxide is a base. You dissolve these two things in water, make them aqueous, they become H plus Cl minus plus Na plus OH minus. That's what they look like in solution. A strong acid, a strong base. So I react those two things together, and the potential products are sodium chloride plus H going to OH. What is that? Water. Water is the product of an acid-base reaction. That's what you get in an acid-base reaction. You get water as your product. Okay? So we get Na plus Cl minus plus H2O. The only thing that actually formed was, because look at these guys. Na plus Cl minus, they're the same on both sides of the reaction, right? They didn't actually form like a solid sodium chloride. They didn't do that. They remained dissolved. So that means they did nothing. They didn't do anything. So they can be eliminated in what we call spectator ions. So the only reaction here for this acid-base reaction is H plus OH minus produces H2O liquid, produces water. Okay? These are the acid ions. This is the acid ion. This is the basic ion. You put an acid with a base, and what do? They neutralize one another. An acid neutralizes a base to form, because it forms water. Water is neutral. It doesn't have an acidic pH, and it doesn't have a basic pH. It's right there in the middle. It's neutral. We're going to look at that more. Okay? Now, oxidation reduction, instead of being the transfer of hydrogen, now actually, if you think about what H plus is for a minute, so hydrogen has a single proton in its nucleus, right? How many energy levels does it have around it? With how many electrons in it? It has one electron in its outermost energy level, right? So that's hydrogen that is not charged. Now if I ionize hydrogen into H+, what's left? No electrons. So what's left? A nucleus with a proton. That's it. That's all hydrogen is. H+ is often referred to as a proton. It's this reactive proton that's just going around and reacting with stuff. That's what H+ is. Okay? It's searching for electrons, that little proton. And it's going to go find it. Okay? So if you have an acid solution, then you're measuring the proton content in that solution. How much free proton is there? How much positively charged proton is in that solution? So acid base is the transfer of this proton from one thing to another thing. Okay? Whereas oxidation reduction is the transfer of electrons. So sodium is a metal, so it loses electrons, right? To Na plus an electron, whereas chlorine gains an electron to become Cl minus. Where did this electron come from? Sodium gave it to him. So when those two things are reacting together, one thing loses an electron, the other thing gains an electron. These are called half reactions. So from these half reactions, we see that we get Na plus Cl plus, and the electrons cancel, I should say, because they're on the both sides of the reaction. You get Na plus Cl minus, which will form NaCl. If it's not in water, it'll actually form that salt. So you take something that's like sodium metal, nasty metal. If you drop it in water, it's going to start to boil, produce sodium hydroxide, big mess. Okay? You don't want that to happen. But if you have sodium, this reactive metal, with chlorine, which is another very reactive gas, it'll kill you. If you inhale chlorine gas, it's going to kill you. Okay? So you take these two things that are very reactive, you put them together, what do they form? They form table salt. Why? Because they've satisfied their octets by doing that. And they were all angry and irritated, and then they find each other and they chill out. And they're like, okay, I like this. Now they're not all that reactive anymore. So table salt.
Bases and acids make salt, right?
Oh, well, this is oxidation reduction. But in acid base, we did make salt as well here. But this was aqueous. These things are still dissolved, but if you evaporated the water, you would end up with sodium chloride, NaCl. Same kind of thing. You have this really reactive acid, right? And you have this really reactive base, a really strong acid, a really strong base. You put them together, they react, and same thing. They form salt water. So, you know, this is scary. This is scary. If you get it on your, either one, if you get it on your hands, it's going to just start to eat away your skin and, you know, all the way to the bone and even the bone. Okay, your finger will fall off. But then it becomes this. And, you know, it's not going to do anything to you except dry out your skin, maybe. You know. So, but it's just salt water. It's not anything scary anymore because those molecules have found their partners and they've become non-reactive. The hydrogen and the hydroxide, they have found each other, and now they're very happy. And now you just have water now. Okay, but it's the same idea, but in two different ways. So this is acid-base. Transfer of protons. This proton gets transferred to this. This is an acid because it donates the proton. This is a base because it accepts the proton, and you form water. Okay. Oxidation reduction. Something is oxidized when it loses electrons. So what lost electrons? Oxidation is loss. Sodium lost electrons. It became oxidized. Well, what was reduced? The thing that gained electrons. In oxidation reduction, you always have something oxidized. You always have something reduced. The thing that is reduced, reduction, is gain. Is the thing that gained electrons. Chlorine gained an electron. So this is how you can remember oxidation reduction. Oil rig. Oxidation is loss. Reduction is gain. Because you have to be able to identify that. You're going to have a chemical reaction, and you're going to have to look at that reaction and identify what has lost electrons, what has gained electrons, and then you're going to have to identify the thing that was reduced, the thing that was oxidized. And we'll take it a step further when we get into it. The thing that is the oxidizing agent and the thing that is the reducing agent. Okay? And that can be kind of tricky. It can be a bit tricky. So we're going to look at how we can figure that out. Okay? All right, so that's kind of an introduction into what we're going to be getting into now. So we were talking about these solutions. You have solutions. Solutions dissolve stuff. And this chapter isn't about solutions, but this is just giving us an idea about how we get these ions. And these ions can be reactive when you put them into solution if you pour something else into it that is also reactive. Okay? So the basics of a solution is it's a homogeneous mixture of two or more substances. A solute is a substance present in the smaller amount. The solvent is substance present in the larger amount. Okay? Solution, a soft drink is a solution, water and sugar, and even carbon dioxide. Okay? So the carbon dioxide is in the solution in a perfect amount. It's homogeneous. Air is a solution. Solvent is nitrogen. There's more nitrogen in the air than any other molecule or gas, and all the other gases are dissolved into it. Oxygen, argon, very small amount. Methane, very small amount. Carbon dioxide probably is more up there with oxygen. Okay, but those are all gases dissolved into air. So, solder, lead is the solvent, and it has tin in it. Okay, and a homogeneous mixture of them, and it becomes solder. Right? So those are examples of these solutions. Okay, electrolytes. Electrolytes are the things that conduct electricity in a solution. So if it's capable of producing an electrical charge, then it's a electrolyte. Non-electrolytes are substances that, when dissolved in water, don't conduct electricity. So let's kind of figure out, well, what are those things? Well, if something is ionic and it dissolves in water, it will conduct electricity because it breaks apart into its ions in solution. They will break apart. Sodium chloride. Sodium chloride, when you put it into water, it dissolves into Na plus Cl minus. And we say this is aqueous now, because they are separated in a homogeneous solution or homogeneous solution throughout the entire water. Okay? So this is my solvent, this is my solute. So they're broken apart. Sodium chloride will conduct electricity. It will conduct electricity, and you'll get this thing. See, a strong electrolyte. Sodium chloride is a strong electrolyte. You would conduct electricity through this water solution, and that light bulb would glow bright because it has a strong ability to conduct electricity through. Okay? A weak electrolyte is something that doesn't dissociate like sodium chloride 100%. So let's take an example of okay, this is acetic acid. Acetic acid, when it's put into water, it dissolves and it will break up into acetate. But only part of it. You see that reverse arrow? You have a double arrow. That double arrow means that that hydrogen does not come off 100%. It comes off and goes back on. Comes off, goes back on. Comes off, goes in equilibrium. It creates an equilibrium of how it comes off and goes back on. It's just going back and forth, back and forth, back and forth. That's how you create a weak electrolyte. Because there's not as many ions present in solution due to the fact that it's going back and forth, it doesn't conduct electricity as well. So you get a weak electrolyte. A non-electrolyte. Non-electrolytes are things that do not dissociate or break apart at all, but they do dissolve in water. So, for example, okay, glucose. Glucose is a sugar. Any sugar is a covalent molecule. There are no metals in this. They're all nonmetals. Carbon, hydrogen, oxygen. It's all nonmetals. And because it's all nonmetals, that means it forms covalent bonds. And covalent bonds do not separate in water. They don't break apart. Now, the individual sugar molecules will break apart from one another, and they will dissolve, but they will not themselves break apart. I don't break the covalent bond here or anywhere. It remains as one single thing. And because it doesn't break apart into ions, it cannot pass electrons from one sugar molecule to another. And because it can't do that, it's a non-electrolyte. So this would be like sugar water. You would not be able to conduct electricity through it. Water itself, H2O. Is that an electrolyte or a non-electrolyte? It's a non-electrolyte. Why? It's covalent. So does water conduct electricity? No, it does not conduct electricity. Right? Does this water conduct electricity? Enhanced with minerals. Yeah, it's going to conduct electricity. Does your tap water conduct electricity? Uh-huh. It's got all kinds of minerals in it, right? So yeah, it's going to conduct electricity. Do you go to the grocery store and buy distilled water? It's not going to conduct electricity. Okay? Drinking water is not distilled water because distilled water tastes really nasty, gross, because it doesn't have the minerals that make it taste good. Your guys are like, water doesn't have any taste. Yeah, it does. Go ahead, buy some distilled water and figure. Go ahead, do a taste test. Which one tastes better? It's because of all the minerals. Does the water in San Antonio taste different than the water somewhere else? Absolutely, right? Tastes different. And you get used to that taste. So that's why with all the drinking water, they put minerals in it. Because otherwise you're like, ooh, I don't like this. Okay? But those will conduct electricity. But pure water itself is a non-electrolyte. Okay? We don't even see the water sugar solution conducting electricity. If water was an electrolyte, then this would conduct electricity. Independent of the sugar, okay? But because sugar and water are both non-electrolytes, it doesn't conduct electricity. Okay. All right. So strong electrolytes are the ones that dissociate 100%. Weak electrolytes, not 100% dissociation. So this is that same example I gave you. Okay, acetic acid dissociating into acetate and acid H+. Okay, it's not a complete process. You see, it's going back and forth, back and forth, back and forth. So there's not as many free ions here as there are here because sodium chloride doesn't have a reverse arrow. It just dissociates 100% and remains dissociated. Therefore, it's a strong electrolyte. Okay, so we're good with that. So here, hydration is a process in which an ion is surrounded by the water molecules. So we can see, well, let me ask you guys. Which ion, the cation ion or the anion, are those? The gray one is what? Cat or an. Does it have a positive charge or a negative charge?
That one has a positive charge, right?
Why?
Water has a bipolar charge.
It does.
That's why it's like solvent or whatever.
That's why it's a solvent.
Yeah. So
Uh-huh.
that one, the negative charge is close to the bottom of the red.
Okay, so this is a positive charge, right? This is the cation ion because the water molecules, the oxygen of the water molecules, have negative charges. They have partial negative charges. And when you put that sodium and that chlorine into water, look what happens to that positive sodium molecule. It gets surrounded by water molecules. It gets ripped apart from chlorine. Sodium and chloride have a strong attraction, a strong bond. It's an ionic bond. It's a very strong bond. But when you put it in water, boom, they get pulled apart. Because all these partially negatively charged waters just surround it and rip it off. And look what happens to the chlorine, the negative anion. All these partially positive hydrogens, boom, they rip that thing off and they dissolve it. They surround it. Okay? And so sodium chloride doesn't stand a chance when it gets in the presence of water. It just gets pulled apart. Okay? Okay, so here's now non-electrolytes are things that don't conduct electricity. Here's examples of strong electrolytes. Strong acids are strong electrolytes like hydrochloric acid, nitric acid, perchloric acid. This is a strong electrolyte for the first hydrogen. There's two hydrogens here. The first one comes off as a strong electrolyte. The second one comes off as a weak acid step, so as a weak electrolyte, because it dissociates only partially. The first one, 100% comes off. The second one, partly. So sulfuric acid, sodium hydroxide, strong electrolyte because the sodium and the hydroxide break apart. So it's also a strong base. It's a strong acid. It's a strong base. It's a strong electrolyte. Barium hydroxide, same thing. Strong base, strong electrolyte. Okay. Weak electrolytes: acetic acid, hydrofluoric acid, nitrous acid, ammonia. Okay, don't even worry about that one. Okay, don't let that confuse you. You see that little symbol that they put there? You can't really see it down here. Pure water is an extremely weak electrolyte, they're saying. Okay, just don't even consider it to be an electrolyte at all. They're saying you can kind of conduct electricity through it. Essentially, you cannot. Okay. And here's some these things are completely non-electrolytes. Okay? Methanol, ethanol, glucose, sucrose. These sugars, the ethanol, the methanol, okay? None of those can conduct electricity at all. They're completely unable to do that. Okay? Okay. Now, so we have a basic idea about solutions and ions. When you put them in solution, you create these ions, these aqueous solutions. And now we're going to look at that in precipitation reactions. How does that facilitate these precipitation reactions? So here, this is kind of the example I gave you earlier. Lead nitrate plus sodium iodide produces lead iodide plus sodium nitrate. Okay? we could have predicted that, right? We could look at that and we could say the lead and the sodium are going to switch places. This is a double replacement reaction. The lead and the sodium switch partners, and you get lead iodide as the only other potential product and sodium nitrate as the only other potential product. Okay? You cannot form iodine nitrate. You can't form that. Or lead sodium or lead sodide. That doesn't even sound right because you could never have that. Okay? So you can't form those because that would be a cation and a cation and an anion and an anion. That could never happen. Okay? So these are the only two potential products that I could get. Now, what I have to ask myself is, are these both actual products? So here, this is the molecular equation. So I figure out what the potential products are. Here, I break it up into its complete ionic equation, the Ionic equation. I break everything apart into its ions. Lead, nitrate, sodium, iodide. And then I have to figure out whether these actually form a product or not. Did lead iodide actually form a product? Yes. It became a solid product. Did sodium nitrate actually form a product? No. It remained aqueous. So now when I write the molecular equation, I can write lead iodide as a solid. This is my product. And sodium and nitrate, these remain dissolved. They are aqueous still, okay, as ions. And then I look at the things that did not participate in the reaction versus the things that do. And I eliminate everything that did not participate. So what's left? This is what's left. Lead 2 plus I2 minus, I minus, produces lead iodide, lead 2 iodide, solid. That is the only reaction that occurred, and we call it the net ionic equation. Okay? You have to be able to write these. You have to be able to write the molecular equation, the ionic equation, and the net ionic equations. You have to be able to identify and write those. Okay? If you're given something even just like this, if you're only given this to start with, you have to be able to figure everything else out. You have to be able to figure out, is lead iodide a solid? And I'm going to show you how to do that. There's a chart that you would use. Okay? But essentially, you could be just given this to begin with, and you'd have to figure all these other things out. Okay? And you can see this lead iodide forms a solid precipitate. This is what it looks like. You put those two things together, and all of a sudden, it just begins to come out a solution. This yellow lead iodide precipitate. It's a solid. A lot of times when people react things together, they would describe it as getting cloudy. And that's because a precipitate is forming. Whenever your solution gets cloudy, you're like, oh, it's still dissolved. No, that's not dissolved. That's a solid thing coming out of solution. And if you let it sit there, it will rain down and it will collect at the bottom of the tube eventually because it's more dense as a solid than the water. And so it will come down and it will settle at the bottom. So whenever it gets cloudy, that's because a precipitate is forming. Sometimes it's colorful, sometimes it's just white. Okay? So you have to be able to recognize that. So this is kind of a more in-depth idea of what's happening. Here you have nitrate, here you have iodine. Okay? I'm assuming, I can't see. Here's your lead, and here's your iodine. This was potassium nitrate, because that's a potassium, that's nitrate. Okay? So the potassium and the nitrate remain dissolved. You can see they haven't done anything. They just remain in the same state they were before, But the lead and the iodines, they find each other and they form a solid salt. They come together and form a crystalline salt and precipitate out a solution. Okay? And that's how you'll find them. Okay, so if we're going to write the net ionic equation, we have to first write the balanced molecular equation. Then, just as we saw earlier, you write your ionic equation showing the strong electrolyte, dissociated into cations and anions. You would then cancel the spectator ions, and then check that the charges and numbers of the atoms are balanced. Okay? And then you can write your net ionic equation. And that's important because if you're given something like okay, what are the potential products of this reaction? Does anybody figure out at least one?
The cations are just going to swap
They are.
places, so you're going to have what,
Magnesium
magnesium hydroxide and calcium.
hydroxide.
And calcium nitrate.
Nitride. Okay. Are these written correctly? So that's right. Those are the right products. But I have to be able to write them correctly. I can't just write it like this. That's not their formulas. What are the formulas for magnesium hydroxide and calcium nitride? Okay. Hydroxide OH has a -1 charge. There we go. That's how you have to write it. Otherwise, it's wrong. You have to be able to write them correctly. Okay? So this goes back to being able to identify these chemical formulas of these ionic compounds. Okay? Because you have to write them in the correct ratios as the products. Okay? Okay. Here we have some precipitation reactions. Okay? So let's go ahead and write the ionic equations and the net ionic equations. They already told us the solid products are this and this. Barium sulfate, calcium phosphate. Those are the solid products. So for the barium chloride plus sodium sulfate, let's go ahead and write the ionic equation. Okay? We have barium. What kind of ion is it? 2 plus. Plus Cl. What kind of ion? -1. Whoops, get ahead of myself. Plus sodium. What ion? Positive 1. Plus sulfate. You guys remember the charge of sulfate? Negative 1. Negative 2. Okay? So these are my ions. What do they form? How am I going to write this? I keep it together, right? I don't break it apart. BaSO4 is the solid product here. So it stays together. What about sodium and chloride? Do they stay together? How do I know? Because it says aqueous. That's how I know. This one is solid, so it stays together. Sodium chloride is not, so it breaks apart. Plus Na plus Cl minus. Okay? Now you should balance this. So we have one barium, one sulfate, one sulfate. One sodium here. Okay? I'm sorry. I'm not doing that correctly. I have 2 chlorines here, so this has to be 2. And I have 2 sodiums here, so I need 2 there. Okay? So this isn't balanced either. Okay? That's the balanced equation. So I have 2, 2, barium sulfate. Okay. So that would be more my... So you see how it's Cl2 here? That means I need 2 Cl minuses. Okay? To have this balanced chemical equation. All right. Now, what are the spectator ions? Those are the spectator ions. What is the net ionic equation? Okay, that's my net ionic equation. And if I'm going to be really picky, I would say that these are aqueous, barium 2 plus. This is aqueous. Well, these would all be aqueous. Okay. And that would be my ionic equation and my net ionic equation. Okay, now try it. Go ahead, you guys try it for the next one. Make sure it's balanced. Okay, so here is my equation. I have K plus PO4 3 minus plus Ca2 plus NO3 minus produces Ca3 PO4 2 because they stay together, okay, plus K plus NO3 minus, okay. Here we have 6 potassiums, 2 phosphates, 3 calciums, 6 nitrates, 1 calcium phosphate, 6 calciums, 6 nitrates. Okay, so that's my balanced my balanced ionic equation. This stays together as a solid. Everything else is aqueous, 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 and aqueous. Okay. Now I just eliminate all those spectator ions. Potassium and nitrate are spectator ions, so they are eliminated. And my net ionic equation then is 2 PO4, 3 minuses, plus 3 calcium, 2 pluses to produce Ca3 PO4, 2, solid. These are aqueous. Okay, and that's how I'm going to write my net ionic equation. So you need to be able to know the charges of those things, what they are. I could predict the charge of phosphate from here. Calcium 2 plus, PO4 3 minus. Okay, from the formula there, I could have switched them back up. Figured out the if I was having a hard time doing it over here, but over here we should see -1, -2, -3. Nitrate, this is 0. Oxygen 0, 0, -1, -2, -1, -2, -3, -1. Okay, that's essentially what we're. These are all -1. Everything. This first column is -1, and then as I go here, oxygen is 0. And then I start back over, -1, -2. Okay, -1, -2, -3. Those are the main ones that you need to learn. Okay, as the ATE ions, the 8 ions. Okay, this is the chart that will facilitate you predicting whether something is soluble or insoluble, which means whether it is a precipitate or not. So if it is a precipitate, that means it is insoluble. If it is not a precipitate, that means it is soluble. So all the things that would not form precipitates are these. These are soluble compounds. The things that would form precipitates are these. These are insoluble compounds. Okay? Soluble compounds, no precipitate. Insoluble compounds, precipitate. Okay? So, how do I read this chart, though? Well, remember, lead iodide was a solid. Well, if I come here to iodine, iodine is a halide. Iodine is a soluble compound. So that's not making sense, right? Because if it's soluble, that means it should not precipitate. But do you see this section right here? Insoluble exceptions. Insoluble exceptions means that they are precipitates. So I look at iodine, and then I come over and I say, what are its exceptions? Well, lead is an exception to the solubility of iodine. So that means lead iodide is a precipitate, is an insoluble product. Okay? calcium phosphate. That's one we just did, right? Calcium phosphate. Phosphates are what? Phosphates are insoluble. So calcium phosphate is a precipitate. Well, we better check because look over here at the soluble exceptions to that. What are the exceptions to the insolubility of phosphates? Where are the alkaline metals? First column. Lithium, sodium, potassium, rubidium, cesium. Those are the alkaline metals. Is calcium, Ca, an alkaline metal? No, it's an alkaline earth metal. So it will, in fact, be insoluble with phosphate. What would not be? What would not be? Sodium phosphate. Sodium phosphate would not be insoluble. It would be soluble. So this would be no precipitate because it is an alkaline metal. Okay? What else could I stick on that phosphate besides an alkaline metal, according to the exceptions? The ammonium ion. So no precipitate. Okay? That would be the ammonium ion. So if I want the phosphate to dissolve, I have to stick one of these cations on it that are soluble. I have to stick a soluble cation on it. And then that would allow it to dissolve. And then I could set up a reaction. What if I wanted to form what if I wanted to make calcium carbonate? Okay, this is a precipitate. It's an insoluble product. If I want to make it, what do I start with to make it? I have to start with something that is a soluble carbonate. Give me a soluble carbonate. Potassium carbonate. K2CO3. Now give me something that is a soluble calcium product. Here's your chart. Here are the anions that are soluble. These are soluble anions. Calcium bicarbonate. Calcium. Calcium bicarbonate. Sodium bicarbonate. You know what sodium bicarbonate is? Baking soda. Okay? But here we're trying to get the calcium, not a sodium. Because the sodium bicarbonate, if I reacted with potassium carbonate, wouldn't do anything, right? Everything would remain insoluble. There would be no reaction because the sodium is an alkaline metal, so when it gets onto the carbonate, nothing happens. So here I need calcium bicarbonate. And what is it going to form? It's going to form calcium carbonate plus potassium bicarbonate. Okay, and this will be my solid product. This is aqueous. This is aqueous. Okay, so I will have a test tube of potassium carbonate and a test tube of calcium bicarbonate, and I will put them together and they will form a solid calcium carbonate precipitate. and it will come out of solution as a solid.
What would the net?
So my net ionic equation, then, I would have to balance this. Oh, I already have 2 bicarbonates. There we go. So now it's balanced. So I have K2, K plus CO3 2 minus plus calcium 2 plus bicarbonate 2 HCO3 minuses produces calcium carbonate solid plus 2K plus 2HCO3 minus. Okay. And then I eliminate the spectator ions. Whoops, sorry. I eliminate the spectator ions. And I'm left with calcium 2 plus CO3 2 minus forms calcium CO3 solid. That's my net ionic equation. Everything else is a spectator ion. Everything else would remain dissolved. Okay? So that's how this chart is going to be employed. That's how you're going to use it. Okay, so here's some, you can see precipitates a lot of times are very colorful. Here we have some cadmium sulfide, some lead sulfide, some nickel hydroxide, some aluminum hydroxide. Okay, so those would all be insoluble compounds. Hydroxides are a lot of times insoluble. So if you're working with a sodium hydroxide solution, you want to make sure that the water you're using is pure water. It doesn't have impurities in it, because if it has impurities in it, then what's going to happen? You're going to start to get all these precipitates coming out. So you're in the lab, you're supposed to be working with sodium hydroxide, and you use tap water instead of the distilled water, the deionized water, and all of a sudden you get all these precipitates. Maybe you're trying to do a titration, okay, which you're going to do later, and you're using sodium hydroxide. Well, you just changed the concentration of your sodium hydroxide because you used tap water, and you've pulled out a bunch of your hydroxide ions, which is your base, and they're gone because now they're solid products that are falling to the bottom of your tube. Okay, so that's one reason you have to be really careful about the type of water you're using, because you could get all these side reactions happening that are undesirable. Okay, like lead. There's not lots, but there's lead in your drinking water. There's just calcium in your drinking water. Calcium hydroxide is a solid product, so you know if you have the hydroxide and the calciums there, they're going to precipitate out, and that's going to not be to your benefit. Okay, so let's classify the following as either ionic compounds as soluble, or classify the following ionic compounds as either soluble or insoluble. Okay, so silver sulfate. Are sulfates, do you think, soluble or insoluble? So let's go back here. Okay, so do you see where sulfates are? Now, do they have exceptions? They actually have quite a few exceptions, right? So is silver one of the exceptions to the solubility of sulfates? Okay, so is this a solid or is it aqueous? It's a solid. So does that mean that it's soluble or insoluble? It's insoluble. Okay. Oh, we already did that one. We just did that one. What is it? Carbonate is what? Okay, let's go back. Carbonates are insoluble. What about calcium carbonate? Is it one of the exceptions? No. No, because the exceptions are only which column? The first column, or ammonium. Okay? Which, look, they're right here. Those are the exceptions. Do you see how these are always soluble? These are always soluble. These are the alkaline metals, and this is ammonium. They don't have any exceptions to their solubility. So if I put that on a carbonate, any of those, they're going to remain dissolved. They're going to be able to dissolve. Okay? But if it's anything other than those, like calcium, it's any other metal, whoops, then it is going to be insoluble. Okay. Hopefully I don't have to go back to answer this one. Soluble or insoluble?
Soluble, because it's an alkaline.
It's an alkaline metal. Alkaline metals are what? Always soluble. Okay? Barium. Hydroxide. What do we know about hydroxides? You guys remember? Are they soluble or insoluble? Hydroxide. Remember, if I have sodium hydroxide and I use dirty water, what am I going to get? A bunch of side reactions. Because hydroxides are insoluble. Okay? Hydroxides are insoluble. Now, we have to be careful about this one. We have to go back. Okay? Hydroxides are insoluble. Is barium an exception to its insolubility? Yes. It is. Even though it's not an alkaline metal. Barium is an alkaline earth metal, but it's the only alkaline earth metal that is an exception. Okay? So, whoops. So this one would still be, soluble. That one would be soluble. Okay? Sodium chloride. Soluble. Potassium carbonate. Why? Potassium is a what? It's an alkaline metal. It's an alkaline metal. Magnesium sulfate. Sulfates are insoluble, are soluble. Is magnesium one of those? Whoops. So it is still soluble. Okay? Magnesium hydroxide, insoluble. That's called milk of magnesia. Has anybody ever taken that? If you haven't, it's fun stuff. You should try some. It's a laxative. Okay. All right, guys. We'll see you.